Hi there and welcome to Lecture 5 for Biostats. So today we're going to be basically looking at confidence intervals. We're going to look at a couple more cases such as for proportions and difference of means, and then we'll get to the idea behind hypothesis tests. So just a reminder about what statistical inference is. So this is where we're interested in answering questions about a population, but we only have a sample, right? And so it's the process of taking the information that we have in a sample, such as the sample mean, the sample proportion, difference between means, difference between proportions, some statistical model that we've built from our sample, and allowing us to go back and saying something about the population and introducing the uncertainty that we have that arises due to the sampling process. So questions that we might be able to ask is, can we estimate what the population mean is, or can we show that there's a difference in prevalence of disease between two populations, or perhaps, between a treatment group and a control group or something like that. So it's a process of starting with a sample, working out some evidence in the sample, so seeing an effect in a sample, and then working back to the population and adding uncertainty around that estimate that we got from our sample to capture what's going on in the population through the sampling process. Okay, so essentially we're trying to incorporate the uncertainty that we get when we take a random sample in order to hopefully say something about the population. Okay, and essentially what we use to do that is knowledge of how sample statistics vary from sample to sample, in particular means. Okay, so we have the central limit theorem that says that for a given population with a given mean mu, we know that the sample means from repeated sampling will follow a normal distribution, right? So if you take samples, you compute the mean of those samples, and if you look at how those sample means are distributed across many replicate samples, you find that they follow that nice bell-shaped normal distribution. And in fact, we can kind of even say how much spread that normal distribution has, and of course what the center is. Okay, and because it's a normal distribution, we can then essentially study the normal distribution and thus sort of know how much uncertainty to add, because we can work out quantiles from a normal distribution. We know that within 95% of the samples that we take is going to have the sample mean within 2 standard deviations of the true population mean. Right, so we can use our rules that we built from knowledge of the normal distribution to apply to many more cases than just populations that look normal, right? We don't care what the population shape is necessarily. As long as we've got a big enough sample size, we can still use the normal distribution, because the normal distribution describes the distribution of the sample mean or the sample proportion, okay? And we can use this in 2 ways, right? Because we know how the sample means are distributed, if we have a claim about what the population mean is, then we can tell if our sample is consistent with that or is extreme compared to that claim by just measuring how far it is away from the claim, right? How many standard deviations it is away from the claim, right? And if it's many standard deviations away from the claimed mean, then we know that our sample does not agree with the claim, right? Because it's super extreme. It's not consistent with the claim. The other way we can do that is do it as if we don't know what the population mean is, right? We can just add enough certainty around our estimate from our sample. For example, we could add plus or minus 2 standard deviations, and we know that that will capture the truth 95% of the time, right? Because 95% of the time, the sample means are within 2 standard deviations of the truth. So if we take our sample mean and we add plus or minus 2 standard deviations, then 95% of the time we'll capture the truth in that interval. Okay, and this is sort of visualizes the idea. We have some population here. This is the age of people at Massey University. These the true population mean, so this is the distribution of the population. And then these are different samples. So we take a bunch of different samples and we compute confidence intervals. So that's what the line is. And you can see that these confidence intervals capture the truth, which is this vertical red line here, same as this line here. Almost always, but every now and then we get a sample that is extreme, just by chance, right? Just due to the sampling process. And even when we add the 95% uncertainty interval, we don't capture the truth. Okay, But of course, 95% of the time we do capture the truth. So 95% of the time we're going to be in one of these happy red samples and capture the truth. 5% of the time we'll get it wrong and be one of these black ones, right? Now, a key thing, of course, is that the 95% rule applies in the long run. It's a property of essentially the algorithm, if you like, the sampling process. It's not a property of a particular interval. So when we have just one interval from one sample, we don't know whether our sample is one of the, this black one which gets it wrong or one of the many red ones that gets it right. But of course, it's more likely to be one of the red ones, right? So 95% of the confidence intervals we compute will contain the population mean. A good interpretation of it is that the 95% confidence interval for a population mean is a given range. So for example, maybe it's 3.4 to 7.6, right? We get some range. This is the range of population means that our data are consistent with. Okay, so essentially it's the range of plausible values in the population that our data would agree with, if you like. Now that's for means. But we can do the same thing for many other things because many other things turn out to be means. Okay, so a proportion turns out to be a special kind of mean when the outcome variable is either 0 or 1. Right? If the outcome variable is 0 or 1, 1 if it's if it's true, if you like, and 0 if it's false, for example, if you're returning a diagnostic test or something, then the mean of those 1s and 0s will be the proportion of positives. Okay, so proportions are a mean. So we can compute confidence intervals for proportions in the same way that we can compute confidence intervals for means. And they take the same form, right? It's the proportion computed by the sample plus or minus the standard deviation of the proportion computed by the sample. The k here is just the level of confidence that we want to be. So for example, if k is 2, right, then we'd be 95% confident because 95% of the time, 2 standard deviations are captured by a normal distribution, right? So 2 standard deviations of a normal distribution capture 95% of the observations. If we wanted to be more confident, so 99.5% confident, then maybe k would be 3. If we wanted to be less confident, k would be less than 2. Okay, so k just basically is your sort of scalar for how confident you want to be. But the formula is otherwise the same, right? It's the sample proportion plus or minus some constant, which is depends on your confidence level, times the standard deviation of that thing. And there's some crazy formula for it, okay? Not too crazy in this case, but there it is, okay? We don't need to remember any formula here. The computer does it for us. So all you'll be seeing is output from the computer and interpreting it. Difference in means also is a mean type object, right? So the difference between two populations is also a mean. It's the average difference. So a similar formula works, right? So you'd compute the difference in means from your sample, and then you plus or minus k, where k is maybe 2 for 95% confident, right? Your confidence level, times the standard deviation of that same thing, of the mean difference, right? So the formula is always the computation from the sample statistic, if you like, the point estimate from the sample, plus or minus k, which is your confidence level, times the standard deviation of that point estimate. It's always the same formula, and here's the formula for difference of means. Okay, again, we don't have to remember the formulas. The computer takes care of it for us. We just have to interpret the output and kind of know how to put the code into the computer so it gives us the right thing. So here's an example. We've got feline haemoplasma infection in cats. Here's the paper if you want to read it. It's getting a little bit old now. But the idea was to assess the prevalence of feline haemoplasma infection in New Zealand domestic cats. So DNA was extracted from 200 blood samples sent to NZVP, the diagnostic lab, for routine haemoplasma screening. And then we were, I think it was Catherine Jenkins here, did a bunch of real-time PCR assays along with Kieran Dittmer, who you probably know, and identified 62 cats out of the 200 that were positive. Okay, and we're asked to find a 90% confidence interval for the prevalence of feline haemoplasma infection in New Zealand domestic cats. Right, so we can very easily work out the prevalence within our sample, right? The prevalence within our sample is 62 positive out of 200, right? So 62 divided by 200. 62 divided by 2 is 31, so this is 31%. is the prevalence, 0.31. Okay, so that would be our best guess at what the population proportion is. Okay, so the proportion of the prevalence of feline haemoplasma infection in all New Zealand domestic cats, but we're going to have to add some uncertainty around that, right? And we want enough uncertainty so that we can be 90% confident. So we do that using prop.test in R, so prop.test for a proportion. And we put, so the first thing we put in is the number of positives, and the second thing we put in is the total sample size. Okay, so 62, 200, and then we also put in the confidence level that we want. Okay, so by default that'll be 95%. So if you don't put it in, it'll be set to 0.95. If you put it in, you can set it to whatever you like, right? So here I set it to 0.9 because we want to be 90% confident. Okay, then it gives you all of this output, similar to t.test, isn't it? We have our sample statistic there, so there's our 31% that we worked out by, in our heads basically, and then we've got the 90% confidence interval here. Okay, so we're 90% confident that the prevalence of feline haemoplasma infection in New Zealand is somewhere between 26% and 37%. Okay, so this is the range 26 to 37% is the plausible set of prevalences among New Zealand domestic cats that agree with the particular sample that we have, okay, that are consistent with that sample that we have. So that's proportions. We can also compare populations. So if we have two populations, then we can compare those populations by taking a sample from each of them. So for example, perhaps we want to compare two breeds of sheep for wool production, and we want to see if one breed produces more wool than the other. So to do that, we could take a sample of each of the sample of sheep of each breed and work out what the average wool production is on each sheep, compute a confidence interval and for each one, and then compare them. Okay. So here's our example. We've got two types of sheep, Coopworth and Romney, and there's the wool weight. And so we took two samples, and we could see that the Coopworth seemed to be larger than the Romneys in terms of wool weight, so they produce more wool. But there's quite a bit of overlap, isn't there? Okay, the distributions are relatively symmetric, but the Coopworth has been shifted up a bit. Okay, so we could compute confidence intervals, couldn't we? We could compute a confidence interval for the Romneys. So if we just take our wool data set and just pull out the Romneys, okay, then we could compute a confidence interval for the Romneys, right? So the 95%, so mean of the Romneys is 4.05 kilos, and the confidence interval is 3.87 to 4.23, right? So we're 95% confident that the wool weight that Romneys produced, on average, is between 3.87 and 4.23 kilos. Again, that's the sort of the range of values that are consistent with our sample. And we could do the same thing for the Coopworths, right? So here we have, again, we subset out just the Coopworths, and we do a t-test on the weight variable there, and we get 4.2 to 4.6. Okay, so again, we're 95% confident that the Coopworths is between 4.2 and 4.6 kilos. Now these don't overlap, do they? Right? This one goes up to 4.23, and this one goes down to 4.19. So there's a single value, such as 4.2, 4.21, that are consistent with both of the Coopworth and Romney values. So there's a single value, you can see it here, just through there, there's a single value of about 4.2-ish that satisfy the Romney, i.e. within the confidence interval for the Romneys, and is within the confidence interval for the Coopworths. So it's plausible that in the population, Coopworths produce 4.2 kilos, and Romneys also produce 4.2 kilos, i.e. they're the same. And, by chance, we've got a sample that's slightly higher for the Coopworth and a sample that's slightly lower for the Romneys. Right? So that is a plausible population mean that is somewhat consistent with our data. Okay, but it's actually fairly unlikely, right? Because in order for it to be 4.2 kilos, it's got to be simultaneously down the low end of the Coopworths and up the high end of the Romneys, right? But it could just as likely be at the low end of the Romneys or the high end of the Coopworths, and we would have seen a really big difference, right? So it's actually quite unlikely to be simultaneously at the low end of the Coopworths and at the high end of the Romneys at the same time in order for it to be the same number, right? It's actually much more likely that the Coopworth is higher than the Romneys. So this is actually not a particularly powerful way of comparing things. It works fine if the confidence intervals don't overlap, because you can easily say that, well, one's bigger than the other because there's no value that kind of is in the confidence interval for both of them. But when they do overlap, you suddenly get the, your conclusion is that, well, they could be the same, but it's actually unlikely because they've got to be sort of at the extreme end of both at the same time, and the right extreme end, right? It can't be at the high end of the Coopworths, because then you'd see a difference, right? Because the high end of the Coopworths is well above the range of the Romneys. Similarly, it can't be at the low end of the Romneys because, again, it's well below the low end of the Coopworths. It has to be at, that particular case of the very low end of the Coopworths and simultaneously the very high end of the Romneys, which is quite unlikely. So in these cases, when we've only got two groups like this, we can use the difference in the means. Instead of a confidence interval for each mean, we compute the difference between the means and do a confidence interval for that. Right? So we compute the confidence interval for a difference between the means. And the idea is that then we can use, a little bit of nice mathematics that says if the two variables have a normal distribution, which they do, right? The sample means have a normal distribution centered on the truth, centered on the population mean and with some spread. So the sample means have a normal distribution. Then the difference between them also has a normal distribution. Okay. And so we can do a different type of t-test, which is this one here. This is the formula version of the t-test, where we have this little formula here with a little tilde character, which is the top left of your keyboard below the escape key. And that just means in terms of. So this is doing a test for is weight, for weight in terms of breed. So weight changing with respect to breed using the wool data. Okay. Then when you do this, it computes the difference. So it computes the mean in the Coopworths and the mean in the Romneys. Right? Those are the same numbers we had before. But now it's also computed the difference between them, which would be about 0.34, right? 0.34 kilos. The Coopworths are heavier than the Romneys by 0.34 kilos. And it's given us a confidence interval for that difference. Right? So we're 95% confident that the difference in average wool weight between Coopworth and Romney, that's Coopworth minus Romney, is somewhere between 0.08 kilos and 0.6 kilos. Right? And so we're saying that we're 95% confident that the Coopworths produce more wool than the Romneys. The amount more might be, 80 grams more, or it might be almost 600 grams more. Right? That's the range. We're 95% confident about that range, and that range does not include the possibility of zero. Right? Zero is outside that range. So our conclusion would be, well, we're 95% confident that they're not the same, that they're different, and in particular, Coopworths are larger than Romneys. Coopworths produce more wool than Romneys, rather. I guess they could be larger as well, I suppose. Right, so we can compute confidence intervals for differences. We can compute confidence intervals for proportions. We can compute confidence intervals for sample means. They're all done essentially in the same way. They're all basically take your sample estimate, that's your best guess, that's the center of your interval, and then add on an amount of uncertainty for which there's a formula, which essentially is basically depends on the standard deviation of that estimate. So we've got some other data. We started looking at this in the last lab as well, lab 5 I think it is. And this is data on bycatch petrels, so caught as part of the fishing process in different geographic areas off the coast of New Zealand. And the question is, might there be different subspecies of petrel depending on the geographic location, right? So here's where they were all captured. Okay, this is the Antipodes Islands out here. I guess the Auckland Island will be down here somewhere, maybe. And then, a bunch off around the coast and so on. And we have a number of measures. We've got an ID number, we've got the year it was caught, the month it was caught, where it was caught, longitude and latitude. Thus I could produce that map, the general area it was caught, and various measurements. So the common depth, the bill least depth, the nostril length, the tarsus length, that's the legs, isn't it? Right and left, the tail length, the right and left wing length, the sex. And when we look at these measurement variables, we see generally the same pattern, right? That the males tend to be larger than the females in all of these measures. Okay, again, there's a lot of overlap, mostly symmetric data. Okay, so we could estimate the difference in wing length by computing a confidence interval for that difference, right? So we can compute a confidence interval for the difference in right wing length between the males and females. And then, of course, if the confidence interval for the difference doesn't contain 0, we conclude there's a difference. And if it does contain 0, we conclude that our data is consistent with there being no difference. So here's the same formula that we saw before for the Coopworth and Romney sheet, right? We've got the formula syntax where we've got our data set coming from the Petrels, and we've got the right wing length in terms of sex. And we see the average in the females is 385.6 and the average in the males is 388.4, so males are bigger than females on average. And we've got a confidence interval for the difference, females minus males. Females minus males is somewhere between minus 5.1 and minus 1.2. So we're 95% confident that the difference in average right wing length between females and males in the population is between minus 5.1 and minus 1.2 millimeters. And because 0 is not an option in there, right, you're either minus 1.2 or sort of larger than minus 1.2 if you like. 0 is not an option, so they must be different. Okay, and males, of course, larger than females because these are negative. This is female minus male, so males bigger than female would give you a negative number. So we're 95% confident that males have larger wings than females by between 1.2 millimeters and 5.1 millimeters. So that's how confidence intervals work, okay, and how confidence intervals can be used to check differences, right? You compute the confidence interval for the difference, and then you see if 0 is an option. The alternate to figuring out if there's a difference between things is to kind of go the other way. So what we do is, instead of computing a confidence interval for the difference, we instead say, well, is 0 a possibility to begin with at all? So what we do is we say, well, let's sort of do a thought experiment. What if there was no difference between the male and female birds in the population and that their right wing lengths were in fact the same on average? What would we expect to get in a sample, right? So essentially we create a hypothesis about the population. So we're going to hypothesize that there's no difference in the population, that male and female birds have the exact same average right wing length. And then we simply say, well, how often would we get a sample from the sampling process, which is going to have uncertainty associated with it, so it's going to, jump about randomly. How often would we get a sample that looks like the one we actually got in our data? Right, so what we do is we think about the potential samples we might have got if our hypothesis holds. Right, so we assume that there's no difference between male and female birds in the population, and then we take a sample. Right, we imagine taking samples. Right, and if there was no difference in the population, then when we take samples, we'd expect to see no difference in our sample, or at least not a very big difference. Right, every now and then we'd see, we'd see a difference. Right, just by chance, just due to the sampling process. Maybe we just, by chance got a few of the heavier males, of the larger males, or maybe we got a few of the larger females. Right, so in some samples, what we'd expect is that the difference between the right wing length between male and females would be maybe positive. The males would be bigger than the females. Sometimes it would be negative. The females would be bigger than the males. Okay, but we'd expect that on average, the difference in our sample should be 0, right? Because in the population, we are hypothesizing that there's no difference. Every now and then, due to our sampling process, we might get a difference that's as big as maybe, say, 3.1 millimeters. 3.1 millimeters being how big we got in our particular data set here. Right? by chance, this could have happened. Okay, what we want to know is how likely is it? How likely is that to happen? And we can figure that out by simply knowing how many standard deviations away from 0, which is our hypothesized value, right? There's no difference is our hypothesis. How many standard deviations away from 0 is 3.1. That's essentially what we do. And then once we've figured out how many standard deviations away from 0 it is, we can then say, well, we know what a normal distribution looks like. You know, how often is it to be, would it happen in a normal distribution that you'd get a sample that's 3.1 standard deviations away from 0? Well, actually, we know that, don't we? Because we know our rules of thumb. Our rules of thumb say that 99.5% of the time, it's within 3 standard deviations from 0, right? And here we have something that's more than 3 standard deviations. It's about 3.1 standard deviations. In fact, 3.2 is that number there, as it turns out. Okay, it's 3.2 standard deviations. So it's kind of more extreme than 3 standard deviations. And we know that 3 standard deviations would, within 3 standard deviations happens almost all the time, 99.5%. So outside of 3 standard deviations must happen less than 0.5% of the time. So it's very rare for that to happen. So our conclusion, if it's very rare, is that our sample must be very extreme. Therefore, our sample was not consistent with the hypothesis of no difference between the population. Instead, our sample was perhaps consistent with there being a difference. Right? So essentially, we kind of do a almost a proof by contradiction, if you like, or we prove it wrong by showing that it's an absurd outcome given the data that we've observed. Okay, so this is basically how it works, right? If the hypothesis holds, then we know how samples should look, right? Because we know how the sampling process looks, right? We get sample means that are, follow a normal distribution, centered on the truth, which in this case is going to be 0, a difference of 0. So the truth is 0, and with a certain amount of spread, right? We know how this happens, so we can kind of assess how extreme each sample is. So here's the process. So here's our true mean mu. So in most cases, this might be equal to 0 for a difference, for example, so no difference. Then we know that 95% of the time, we're going to get sample means that are within 2 standard deviations away from mu. But sometimes we're going to get one, 5% of the time, we're going to get an extreme one, like this red one out here. Okay. And we can see how extreme it is just by seeing how far it is away from 0. Right? This one here is really close. This one here is a bit further away in the positive direction. This one here is a long way away. And that's what this column of numbers here. It's just how many standard deviations the point is away from the hypothesis. So this one's very close, right? We've got 0.08. Here's another one that's very close, 0.11. Okay, but this one's very far away, 3. Okay, and then we convert that to a probability, which is the P column here, which is basically measuring how extreme is this. So how often would we expect to get something this extreme or more so? So when we have a small number, our p-value is large, right? Because we'd expect to get something as large as this tiny difference we observe here or bigger almost all the time, right? We'd expect to see that 93% of the time. We'd expect to see something as with a difference as large as this one here, which is 0.75 standard deviations, almost half the time, right? So all of these ones are really typical, and we see they have typical p-values that we'd expect to happen all the time. This one here is very abnormal, it's far away, and we have a very small probability of observing that. So P is the probability of observing the particular sample under the assumption of the hypothesis. Okay. So in our Petrels, then if our hypothesis is that there's no difference between the females and the males, right, then we would compute, then we'd work out what our sample statistics are, and we'd compute the difference between them, and then we'd say how extreme is that. So this here, 3.2, that's the number of standard deviations our difference between females and males is away from the hypothesis of 0, that's called the test statistic. So the test statistic is basically just how many standard deviations you are away from the hypothesis. The p-value then here tells us how likely that is to occur. Okay, so this is a very small p-value, 0.001, so that's less than 1%, right? 0.15%. So it's very so it's saying that this sample is very extreme compared to the hypothesis of no difference. So it'd be unlikely to get a sample like this, like the one we got, with a big difference of 3.2 millimeters. It'd be unlikely to get that just due to chance, just due to the sampling process. Okay, so our conclusion would be that the data that we've seen here is inconsistent with that hypothesis. Right? Our data is inconsistent with the hypothesis of no difference between male and female. Therefore, our data is providing evidence against that hypothesis. Okay. Right, so our sample is extreme. Right, it's got a large test statistic. And the p-value, which is the thing we really use, right? We don't really use the test statistic. It just happens to be an interpretable measure in this case. We use the p-value to see how extreme that is. Okay, in other cases that we'll look at later on, the test statistic won't have a meaningful value, such as the difference between the males and the females, for example. It might be mean some other thing that we perhaps it takes longer to explain, but we'll still have a p-value, right? The p-value can be interpreted in the same way, regardless of context. So that's the nice thing about it. So, so this is our particular sample, and our sample, or something more extreme, would be expected to happen very infrequently. Okay, hardly ever, due to sample variation. And this isn't very likely, right? It's a low p-value, so our data are inconsistent with the hypothesis. Therefore, we conclude that there's a difference between male and female in the population. So hypothesis testing takes this kind of backwards approach, where you kind of we're wanting to show there's a difference between male and female. So what we do is we start by saying, well, let's pretend there's no difference, and then we look at our data and say, well, we saw a difference in our data. How could that be? Well, it could be due to the sampling process, right? Due to the random variation around sampling. And so we work out, well, how likely is it to be due to the sampling process? That's the p-value. And if it is unlikely due to the sampling process, so if the p-value is really, really small, then we say that, well, it's probably not due to the sampling process. It's probably due to, in fact, our hypothesis being wrong, right? It's probably due to the fact that actually there is a difference between male and female in the population, and what we see in our sample is just a reflection of the population. So it's not that we've just got a kind of a freak sample. It's a possibility that we got a freak sample, but that possibility is very low. So we kind of discount that possibility and therefore suggest that in fact there's a difference. So it's this backwards thing where to show there's a difference, we start off by saying, let's assume there's no difference, and then we prove ourselves wrong. Okay. Right, so this just basically says that. So a hypothesis test provides evidence as to whether a hypothesis about a population parameter might hold. The p-value of the hypothesis test is a measure of how likely it would be to get a sample with a statistic as large or larger than we observed in the one we have, due to sample variation. So if the p-value is really small, then our sample is inconsistent with the hypothesis. If our p-value is large, then our sample is typical of what we've seen, and therefore consistent with the hypothesis. Right? So is the hypothesis true or not comes down to, is p large or small? If it's small, then we'd say that the hypothesis of no difference is probably not true, because our sample is showing a difference and is unlikely. If our p-value is large, then even if our sample is showing a difference, it's sort of the typical difference that we might see from sample to sample variation. So our data are consistent with the hypothesis. Okay. So hypothesis tests and confidence intervals essentially answer the same question from a different approach, right? So a confidence interval uses a statistic from the sample to give a range of plausible values for the population. And because we give a range of plausible values for the population, we can answer claims about that population by seeing whether the value is inside our plausible range or not. A hypothesis test is different. You take the claim and then you see how likely, you could sort of assume that claim is true and say, if it's true, how likely would it be that I observe my data? That's the p-value. And if the p-value is small, then you're saying, well, if the hypothesis is true, it's super unlikely that I'd get the data that I have in front of me. Therefore, my data is not consistent with that hypothesis. So it provides evidence against the hypothesis. Okay, and it precisely quantifies, the p-value precisely quantifies how much evidence, right? Okay, so the general process for a hypothesis testing is we consider a hypothesis of no difference, right? So for example, there's no difference between male and female petrel right wing lengths, or there's no difference between Coopworth and Romney's in terms of the wool production. We then take a sample and we estimate the same thing in the sample, right? So we'd estimate the difference between right wing length between the male and females in our sample, or the difference in wool production between Romney's and Coopworth in our sample, right? We then see how often would that happen given what we know about the sampling process. So we use our knowledge about the sampling distribution, right? That the sample mean, or the difference between the means, is going to be normally distributed with some standard deviation, and we use that to compute a p-value. If our p-value is large, then our sample is typical. It's something that we'd expect all the time, right? The p-value tells you how often you would expect your sample, given the hypothesis is true. So if you get a large p-value, you're saying something like this could happen all the time. So our data is consistent with the hypothesis. If your p-value is small, on the other hand, then what you're saying is, actually our sample is quite rare. It's kind of extreme. I wouldn't expect that all the time at all. In fact, I'd expect it hardly ever. So your data is inconsistent with the hypothesis, right? So small p, you have evidence against the hypothesis because your data are inconsistent with it. Large p, your data is consistent with the hypothesis, so sure, the hypothesis might be true. At least our data are consistent with it, okay? So going back to it, we have our t-dot test, we have our p-value here, okay? So there's only a very small chance, 0.15%, that we'd observe this difference, or a bigger one, in our sample if there was no difference at all in the population. Okay, this is rare, so our conclusion would be that we have evidence against the hypothesis of no difference, right? So our sample is not consistent with there being no difference in the population. And that, of course, is the same conclusion as we get from the confidence interval. So our confidence interval is telling us there's a difference, and it's somewhere between 5 and 1 units. Our p-value is also telling us there's a difference. It's not telling us how big it is, though. Instead, it's telling you what's the chance that you'd see this data if there was no difference. So it's sort of precisely quantifying the evidence against the hypothesis. Okay, so confidence interval gives you an estimate of what the parameter is in the population, so what the difference is. Tells you how big the effect is. The p-value is sort of a statistical measure that shows you how unlikely you'd get, how likely it is to get your data if the hypothesis was true. Okay. In general, the confidence interval will be more useful to you because it quantifies the size of the effect. But the p-value is sort of a measure that's very easy to grade on importance, if you like, right? Smaller p-value, there's more going on, at least from a statistical sense. Okay, so we'll see how to use these two things as we go on, particularly when we get to linear modeling. Okay, in general, you should prefer confidence intervals over p-values, but sometimes p-values are kind of a way to sort of prioritize things before you start looking at effect size. That's it. So remember, inference is the process of going from sample to population, and we can do that two ways. We can do it with a confidence interval, right, which takes from our sample and gives you an estimate of what the corresponding value is in the population, along with an uncertainty range, right? So it gives you a range of plausible values in the population. Hypothesis tests, on the other hand, you take a claim about the population and you see whether your data are consistent with it by computing the p-value. The p-value is the probability that you'd observe your data if that hypothesis was true. Okay? Both of them are essentially allowing you to answer questions about the population in two different ways. One of them allows you to quantify how much evidence do I have in my sample about the hypothesized population parameter, And the confidence intervals are saying, what can I say about the population parameter given what I see in my sample? Okay, so they're related, but sort of approaching things in two different ways.